Okay, the section's about differentials. And not to be taken lightly. It seems like when I was taught differentials, it wasn't emphasized enough. You see it again, the differentials in Calc 3, where you sort of are forced to deal with them in order to, it seems like when you're defining differentiability, you have to know about differentials. But anyways, let's take a look here and just see what the book has to offer us. So they'll begin with tangent line approximations. Okay. So we'll learn in Calc 2 that you can make pretty good approximations of functions so long as they have a bunch of derivatives. You can get linear approximations, quadratic approximations, et cetera, et cetera. So this is kind of a first taste of that issue. So let's say I have a point here, C, and then a point on the graph is at C, comma f of C. Okay? And then I want to approximate this graph in this little area around C with this tangent line. You can see as we're getting close to C, the tangent line is kind of going to be a lot closer to the actual f of C values. Okay, over here, we sort of get away from whatever value it is. So let's say x1. Way over here, the height value on the graph will be different than the height value on the actual function. The differential part of this section will be interested in the difference between the actual change in y and the change in y from the tangent line approximation. So as you go from here to some point over here, like c plus change in x, there's a change with the height of the tangent line. So there'll be this little change in height here. But then there'll also be sort of an official change in height called change in y. Okay. The little change in height when we consider the tangent line will be dy. That will be the actual differential. So this length right here, I'm sorry, it's off tilt a little bit, but this length right here will be dy, the differential. And we'll try to approximate the actual change in height with this little change in height. Okay, this change in height of the tangent line approximation. Okay, so anyways, what is the tangent line approximation? Well, we can use the derivative for the slope and then use this point c comma f of c for our point, and then you just use the point slope formula. You know, y minus y1 equals m times x minus x1. So in this case, y minus f of c equals f prime of c times x minus c. And then we're going to move the f of c to the other side. Okay, so y equals f of c plus f prime of c times x minus c. And then you can sort of continue, there's a pattern going on here, which you can continue on, which you'll do once you get to Calc 2, which is kind of neat. So you would have something like f of c plus f prime of c times x minus c plus f double prime of c times x minus c squared, kind of, right? And then there'll be this factor we have to worry about all over 2, and then plus on and on and on. You can pull that off. So long as the function has these derivatives, you can kind of pull this trick where it's just an extension of linear approximation. Okay. So anyways, the book will have you go through problems like number 5. Let's do something like number 5, because number 5 is a bit unrealistic. Let's say we have f of x equals sine of x, and we want to approximate sine of x in some interval and at some point, right? Centered at some point, an interval centered at some point. So let's use a point such that we know how to evaluate sine of x. So for instance, pi over 3. So we know that, we learned that from reference angles in trig. The sine of pi over 3 is radical 3 over 2. Okay, so putting it back into this context, we have f of x sine, and then we need an f prime of x, which will be cosine of x, and then we need our f prime of c, and then c comma f of c. So f prime of c, and our c value here, our center, is going to be pi over 3. Okay, so we'll have the cosine, which equals then the cosine of pi over 3. Sorry, I should say equals in there. And the cosine of pi over 3 then is 1/2. And so we have our point and we have our slope there, so we can create a tangent line equation to approximate f of x at this point, pi over 3. So I'm going to call it t of x, and it'll equal f of c. So f of c is radical 3 over 2. And then plus f prime of c, which is 1/2, times x minus c, which is pi over 3. Okay? So if you want to rewrite it, we're going to be putting it into our calculator, which we won't have to get up and run over and get it because it's on the other side of the room. Radical 3 over 2 plus, well, let's just leave it like that. I mean, that's sort of the form we want anyways, so let's leave it like that. I'm going to get my calculator. Okay, we want to sort of compare the tangent line approximation to the function, actual values of the function, in a small interval around pi over 3. So we'll make a chart. So x, f of x, and then t of x. Okay. So the exact center, we have x is pi over 3, and then f of x will be radical 3 over 2. Okay. So if you put pi over 3 into our tangent line equation, you'll see pi over 3 minus pi over 3 is 0, times 1/2 is 0, plus radical 3 over 2. So at that point, awesome. It's exactly the same, and there's no issues there. But let's start looking at little changes in either direction on the other side. So let's say pi over 3 plus 0.001. Okay, so let's test 1.0482 radians and put it into each character here. So let's do this. The sine of that value, so second sine of answer gives me 0.866525 about. And then I'm going to store my tangent line into my y equals menu right now. So radical 3 over 2 plus 1/2 times x minus pi over 3. Oops, it's not happy about something. Looks like I need a parentheses over here. 3 over 2. Okay, it's happy now. And let me then put that in there. So second y1 of this thing equals almost exactly the same still. So 0.866525. Yeah. Let's move a little farther away from that point. So pi over 3 plus 0.01. Okay. So that x value 1.0572. And let's see what the output is for sine. So second sine of that. So you get 0.870982. And then let's do it down here as well, using my tangent line approximation. And it's starting to get different. So 0.871025. Okay, so the point is, as we move away from whatever center we've chosen, the tangent line in all likelihood is going to kind of go away from the original graph, unless the original graph was just a straight line. Okay. All right, so you know, it's going to be a good approximation close, but as you go farther and farther away from pi over 3, it's not going to be very pretty. So let's go farther away in this other direction and see what we get. So let's try pi over 6 and see what happens. So sine of pi over 6, of course, is 1/2. Let's get the tangent line at that point. And it's not bad, but it's not good either. So 0.604 for our approximation there. And that's, no, that's not going to be good enough. Only horseshoes and hand grenades, right? That'll be nice. So anyways, there's that idea. We're going to explore it a lot more in Calc 2. For now, we want to go back to this idea of the differential, the difference between the difference in the actual y values and the difference in the y values generated by the tangent line approximation. Okay. Okay, so differentials. And when I first started learning about this, it really helped to go back and take a look at the history of math and just study how Leibniz and Newton both approached the problem. And if my memory serves me right, and I bet it doesn't, but let's just for the sake of something to talk about, I guess, we could say that Newton, I think, was more of the flavor where he would kind of look at the change in x and the change in y separately. So maybe he would, if you had, what was his weird notation? You have like y dot equals, well, if, let's start with if y equaled x squared, he would say y dot equaled, there would be a dot over the y dot equals 2x times x dot. So the change in y is kind of proportional to the change in x by a factor of 2x. And he would keep it separate like this, as opposed to writing it like Leibniz would have, dx over dy equals 2x. Okay. So I mean, that's what how I kind of make my mind go to sleep at night and thinking, and okay, this differential stuff's more in the flavor of Newton than in Leibniz. Keep the stuff separate. Keep the dy over here, the dx over here, and work with it that way. I think the only problem is well, I don't know. Okay, so anyways, if you're really interested, go back, and, don't take my word for it. I'm just going by memory here. Go back and, Google the Leibniz and Newton and the history of derivatives and see what you get there. Okay, so anyways, let's make the differential defined a little bit more exactly. And we'll do it in terms, I'll start with sort of a geometrical interpretation here. Is some sort of curvy type function, f of x, and we'll consider the 2 points, the y values at 2 points, c, and then change in x, c plus change in x. Okay, so this point here would be c comma f of c, of course, and then this associated point here would be c comma f of c plus change in x. We are interested in the difference between the actual change in y, which is this height here. Okay, so this is change in y, delta y. And the other height, change in height we're interested in is the change in heights of the points on the tangent line. So if I have my tangent line here going in this direction, I can approximate the height at f of c plus change in x by using the tangent line point here. Okay, and this other distance from here to here is going to be the differential. Okay, so this distance from here to here, which I'll rewrite over here is the differential. Okay. So what we'll be doing here in the applications is approximating this change in y with the differential dy. Okay, so what are those things? Algebraically speaking, the change in y is the difference between f of x plus change in x and f of x. Okay, so clearly that's true. To get the differential, then, we can consider the tangent line. So this point right here, if we were to kind of extract it and take a look at it, so let me draw an arrow. What is that point? Well, it's c plus change in x, comma, t, the tangent line of that point, c plus change in x. Okay. So we can approximate then this change in y by looking at the difference between the tangent line value at that point and the original, f of c. Sorry, these should be c values here. Okay. Okay, so what is this thing exactly then? If I go back to my previous definition here, I can substitute this c plus change in x in wherever I see an x, and then rewrite the tangent line thing. So this y here is actually the t of x formula that we're dealing with. So t of c plus change in x is going to be f of c plus f prime of c times x minus, and x should be not x, but rather c plus change in x now, c plus change in x minus c, and then f of plus f of c, minus f of c, sorry. So this part of it, I'm running out of room. Okay, let me rewrite that. So it's equal to f of c plus f prime of c times c plus change in x minus c minus f of c. Okay. Okay, you can simplify this considerably, and what's going to happen, we're going to get the formula that we need for the differential. Okay, so f of c minus f of c is 0, c minus c is 0, and we're left with f prime of c times change in x, which is what we're going to be using, okay, for our differential. So let's make that now clear. Dy is equal to f prime of x times dx, okay? And that is the differential of y. For change in x, we're going to note that dx is exactly the same thing as change in x. Okay? And so here now we're going to be approximating change in y with the differential of y. Okay. Okay, so the sort of application universe where this would come in handy is kind of a clever trick that you use to evaluate certain expressions, certain numerical expressions. And you'll see this again once you get into Calc 3. So let's look at 42, and we have the cube root of 26, and we want to evaluate this basically without a calculator, which seems insane, but we can do that now. So we note, or we recall from before, this differential formula, change in y is going to be equal to f of c plus change in x minus f of c. And then we can, what can we do? We can approximate f of c plus change in x with, so I can rewrite this, f of c plus change in x equals change in y minus, or rather now plus f of c. And then we can approximate that using the differential. So dy plus f of c. Okay, okay, so this is the concept that we're going to apply to this problem here. And we first are going to note what is our f of x. And of course, that's going to be the cube root of x. We want to center it at a value that we know how to evaluate. So in particular, we want to center it at the point, well, what? 27, comma 3, because the cube root of 27 is 3. Then we're going to say, okay, f of our c value, 27, plus our change in x, which in this case will have to be -1, because that'll give us positive 26, which is what we're trying to figure out. This will then be approximately equal to the differential of y, so I'm going to need the derivative of f of x. And what am I doing? I'm going from this formula here. Okay? So I need to put this material in right here. So the dy part from before is f prime of x dx. Okay? So I need f prime of x to accomplish this. F prime of x, use the power rule, bring down the 1/3. You'll have x to the 1/3 minus 3/3 is -2/3, which is 1 all over 3x to the 2/3. Okay, so for dy, I need this part, f prime of x, times the change in x. And the change in x is going to be -1. So maybe I should recognize that as well. Change in x is -1. Okay, so you'll have in this blank here 1 all over 3 times 27 to the 2/3 times change in x, which is -1, plus f of c. So our center c is this 27 right here. Sorry, it's getting a bit crazy. The c value is right there. So plus f of c, in other words, the cube root of 27. Okay, so the great thing about all of this is we can do this in our head. Take this and evaluate, right? So the 2/3 power of 27, the cube root of 27 is 3, and then squaring it is 9. So I have 1 over 3 times 9 is 1 over 27, times -1 is negative. And then plus the cube root of 27, which is, of course, 3. Find a common denominator. And then add the numerators over the common denominator, and you have your approximation for the cube root of 26 without ever having to pick up a calculator. Okay, so I've heard of stories of old guys in the field, older engineers that are able to handle cube roots in their head just based off of this method. Can I believe it? Ripley's Believe It or Not, right? Okay, right. What else is there application-wise? Well, we have error propagation rearing its ugly head here as well. So I think I'm in section 3. So we'll sort of call this error propagation. And the deal is you have a machine shop or something like that where they have to measure things by hand with physical calipers, things like that. And you expect there's going to be at least a very minute amount of error. Okay, so the error propagation will say there's going to be an exact value of measurement. Okay, so maybe I'm measuring I don't know what they measure, nuts and bolts, the top of a bolt, and the person makes a measurement, maybe let's call it human measurement, is X. And then there's this actual measurement. Okay, so the actual measurement, so if you had some sort of, I don't know, what would do the measurement, some electron microscope or something, the actual measurement is considered to be X plus change in X. Okay, And this change in x part then is the measurement error. Okay. Error. Okay. Okay. So the error propagation is looking at the difference between using the error measurement in some sort of compounded calculation and the actual measurement in some compounded calculation. In other words, if we had to take this measurement and put it into some sort of function, so we'll say f of x plus change in x is where we really want to be at, but the human measurement, using that, we get f of x. This difference is going to be the propagated error, change in y. Okay? So then this is our propagated error. Okay, so what we're going to be doing then is approximating the propagated error with the differential. And let's look at problem 29 in the book. We're measuring the sides of a rectangle, apparently. It's on page 272. Number 29, the measurement of the side of a square floor tile is 10 inches with a possible error of 1/32 of an inch. Use differentials to approximate the possible propagated error in computing the area of the square. Okie dokie. So part A, find the propagated error. With the differential. Okay. Let's draw a picture here. So we have a square, and we want our actual measurement to be 10. Well, the actual sort of value is supposed to be 10. And then it says a possible error of 1/32 of an inch. Okay, so our change in x is going to be plus or minus 1/32 of an inch. And we want to get the, what does it say? Use differentials to estimate the possible propagated error in computing the area of the square. So the area of a square is just going to be the sides multiplied by each other. So x squared. Let's go ahead and get the differential. So dA is equal to 2x dx, or delta x in this case. The x value 10. Okay. So we got 2 times 10 times the delta x, which is plus or minus 1/32. And then we'll multiply this together and get approximately, well, not approximately, but 0.625 inches squared, plus or minus. Okay, other things they may ask you for is percent error. So part B, find the percent error. Okay, so to get the percent error, all you're going to do is take the differential and divide by the area. So let's take a look at that. It'll be 2x change in x divided by x squared. So this formula will be 2 change in x all over x. Putting in our information, we have 2 all over x, which is 10, times plus or minus 1/32. And that will equal 0.00625. This is the relative error, and it's plus or minus. And then if you multiply that by 100, you get the percent error. So plus or minus 0.625% is the percent error. Okay, so let's look at sort of a non-application, but will be an application for us, the differential form. So usually when I do my integrals later on in the next section, I'm going to be using differential form for substitutions. So very quickly, how does this going to work? You'll have some expression like y equals x squared, and then instead of going y prime equals 2x as before, the differential form will be dy equals 2x dx. Right? So it's this idea, which I think of as Newton's idea, is just keep the differentials separated so you don't have to worry about dividing by 0 or anything crazy. So I think that's what it has to do with. So let's take a look at the Leibniz sort of version of this. And I said in class, I mean, these two symbols are equivalent. Naively, you can think, okay, all I have to do is multiply both sides by dx, and then you have it, right? So you have dy equals 2x dx. Technically not correct, but that's a great way of remembering it. Okay, so that is the differential form. So let's take a look at another example. Y equals cosine x, so dy will equal negative sine x dx, and that's your differential form. Is there anything else we want to look at? That's about it. Okay, so okay, that's about it. Thank you. Bye.